In mathematics, an equivalence relation is a binary relation that is at the same time a reflexive relation, a symmetric relation and a transitive relation. As a consequence of these properties, an equivalence relation provides a partition of a set into equivalence classes. Notation. Although various notations are used throughout the literature to denote that two elements A and B of a set are equivalent with respect to an equivalence relation R, the most common are A_B and AB, which are used when R is the obvious relation being referenced, and variations of A_RB, ARB, or ARB otherwise. Definition. A given binary relation tilde on a set X is said to be an equivalence relation if and only if it is reflexive, symmetric and transitive. That is, for all A, B and C in X. A_A. If A_B then B_A. If A_B and B_C then A_C. X together with the relation tilde is called a setoid. The equivalence class of under tilde, denoted, is defined as examples. Simple example: let the set have the equivalence relation. The following sets are equivalence classes of this relation. The set of all equivalence classes for this relation is equivalence relations. The following are all equivalence relations. Has the same birthday as on the set of all people. Is similar to on the set of all triangles. Is congruent to on the set of all triangles. Is congruent to modulo n on the integers. Has the same image under a function on the elements of the domain of the function. Has the same absolute value on the set of real numbers. Has the same cosine on the set of all angles. Relations that are not equivalences. The relation between real numbers is reflexive and transitive, but not symmetric. For example, 7 5 does not imply that 5 7. It is, however, a total order. The relation has a common factor greater than 1 with between natural numbers greater than 1, is reflexive and symmetric, but not transitive. The empty relation R on a non-empty set X is vacuously symmetric and transitive, but not reflexive. The relation is approximately equal to between real numbers, even if more precisely defined, is not an equivalence relation. Because although reflexive and symmetric, it is not transitive, since multiple small changes can accumulate to become a big change. However, if the approximation is defined asymptotically, for example by saying that two functions f and g are approximately equal near some point if the limit of f minus g is 0 at that point, then this defines an equivalence relation. Connections to other relations. A partial order is a relation that is reflexive, antisymmetric, and transitive. Equality is both an equivalence relation and a partial order. Equality is also the only relation on a set that is reflexive, symmetric and antisymmetric. In algebraic expressions, equal variables may be substituted for one another, a facility that is not available for equivalence-related variables. The equivalence classes of an equivalence relation can substitute for one another, but not individuals within a class. A strict partial order is irreflexive, transitive, and asymmetric. A partial equivalence relation is transitive and symmetric. Transitive and symmetric imply reflexive if and only if for all X, there exists a Bx such that A_B. A reflexive and symmetric relation is a dependency relation, if finite, and a tolerance relation if infinite. A preorder is reflexive and transitive. A congruence relation is an equivalence relation whose domain X is also the underlying set for an algebraic structure, and which respects the additional structure. In general, congruence relations play the role of kernels of homomorphisms, and the quotient of a structure by a congruence relation can be formed. In many important cases, congruence relations have an alternative representation as substructures of the structure on which they are defined. E.g., the congruence relations on groups correspond to the normal subgroups. Well-definedness under an equivalence relation. If tilde is an equivalence relation on X, and P is a property of elements of X, such that whenever an X tilde Y P is true, if P is true, then the property P is said to be well-defined or a class invariant under the relation tilde. A frequent particular case occurs when f is a function from X to another set Y. If x1 tilde x2 implies f equals f, then f is said to be a morphism for tilde, a class invariant under tilde, or simply invariant under tilde. This occurs, e.g., in the character theory of finite groups. The latter case with the function f can be expressed by a commutative triangle. See also invariant. Some authors use compatible with tilde, or just respects tilde, instead of invariant under tilde. More generally, a function may map equivalent arguments to equivalent values. Such a function is known as a morphism from tilde A to tilde B. Equivalence class, quotient set, partition. Let. Some definitions. Equivalence class A subset Y of X such that a tilde B holds for all A and B in Y, and never for A in Y and B outside Y, is called an equivalence class of X by tilde. Let denote the equivalence class to which A belongs. All elements of X equivalent to each other are also elements of the same equivalence class. Quotient set, the set of all possible equivalence classes of X by tilde, denoted as the quotient set of X by tilde. If X is a topological space, there is a natural way of transforming X tilde into a topological space. See quotient space for the details. Projection. The projection of tilde is the function defined by which maps elements of X into their respective equivalence classes by tilde. Theorem on projections. Let the function f x b be such that a tilde b f equals f. Then there is a unique function g x tilde b such that f equals g pi. If f is a surjection and a tilde b f equals f, then g is a bijection. Equivalence kernel. The equivalence kernel of a function f is the equivalence relation tilde defined by. The equivalence kernel of an injection is the identity relation. Partition. A partition of X is a set P of non-empty subsets of X, such that every element of X is an element of a single element of P. Each element of P is a cell of the partition. Moreover, the elements of P are pairwise disjoint and their union is X. Counting possible partitions, let X be a finite set with n elements. Since every equivalence relation over X corresponds to a partition of X, and vice versa, the number of possible equivalence relations on X equals the number of distinct partitions of X, which is the nth Bell number Bn, where the above is one of the ways to write the nth Bell number. Fundamental theorem of equivalence relations. A key result links equivalence relations and partitions. An equivalence relation tilde on a set X partitioned X. Conversely, corresponding to any partition of X, there exists an equivalence relation tilde on X. In both cases, the cells of the partition of X are the equivalence classes of X by tilde. Since each element of X belongs to a unique cell of any partition of X, and since each cell of the partition is identical to an equivalence class of X by tilde, each element of X belongs to a unique equivalence class of X by tilde. Thus there is a natural bijection from the set of all possible equivalence relations on X and the set of all partitions of X. Comparing equivalence relations. If tilde and a two equivalence relations on the same set S, and a tilde B implies a B for all A, Bs, then is said to be a coarser relation than tilde, and tilde is a finer relation than. Equivalently, tilde is finer than if every equivalence class of tilde is a subset of an equivalence class of, and thus every equivalence class of is a union of equivalence classes of tilde. Tilde is finer than if the partition created by tilde is a refinement of the partition created by. The equality equivalence relation is the finest equivalence relation on any set, while the trivial relation that makes all pairs of elements related is the coarsest. The relation tilde is finer than on the collection of all equivalence relations on a fixed set is itself a partial order relation, generating equivalence relations. Given any set X, there is an equivalence relation over the set XX of all possible functions XX. Two such functions are deemed equivalent when their respective sets of fixed points have the same cardinality, corresponding to cycles of length 1 in a permutation. Functions equivalent in this manner form an equivalence class on XX, and these equivalence classes partition XX. An equivalence relation tilde on X is the equivalence kernel of its surjective projection pi XX tilde. Conversely, if a surjection between sets determines a partition on its domain, the set of pre-images of singletons in the codomain. Thus an equivalence relation over X, a partition of X, and a projection whose domain is X, are three equivalent ways of specifying the same thing. The intersection of any collection of equivalence relations over X is also an equivalence relation. This yields a convenient way of generating an equivalence relation. Given any binary relation R on X, the equivalence relation generated by R is the smallest equivalence relation containing R. Concretely, R generates the equivalence relation A tilde B if and only if there exist elements x1, x2, xn in X such that R equals x1, B equals xn, and R or R, I equals 1, n1. Note that the equivalence relation generated in this manner can be trivial. For instance, the equivalence relation tilde generated by any total order on X has exactly one equivalence class, X itself. Because X tilde Y for all X and Y, any subset of the identity relation on X has equivalence classes that are the singletons of X. Equivalence relations can construct new spaces by gluing things together. Let X be the unit Cartesian square 0, 1 times 0, 1, and let tilde be the equivalence relation on X defined by A, B, 0, 1, tilde tilde. Then the quotient space X tilde can be naturally identified with a torus. Take a square piece of paper, bend and glue together the upper and lower edge to form a cylinder. Then bend the resulting cylinder so as to glue together its two open ends, resulting in a torus. Algebraic structure. Much of mathematics is grounded in the study of equivalences and order relations. Lattice theory captures the mathematical structure of order relations. Even though equivalence relations are as ubiquitous in mathematics as order relations, the algebraic structure of equivalences is not as well known as that of orders. The former structure draws primarily on group theory and, to a lesser extent, on the theory of lattices, categories, and groupoids. Group theory, just as order relations, are grounded in ordered sets closed under pairwise supremum and infimum. Equivalence relations are grounded in partition sets, which are sets closed under bijections and preserved partition structure. Since all such bijections map an equivalence class onto itself, such bijections are also known as permutations. Hence permutation groups and the related notion of orbit shed light on the mathematical structure of equivalence relations. Let tilde denote an equivalence relation over some non-empty set A, called the universe or underlying set. Let G denote the set of bijective functions over A that preserve the partition structure of A, X A G G, X. Then the following three connected theorems hold. Tilde partitions A into equivalence classes. Given a partition of A, G is a transformation group under composition, whose orbits are the cells of the partition. Given a transformation group G over E, there exists an equivalence relation tilde over E, whose equivalence classes are the orbits of G. In sum, given an equivalence relation tilde over E, there exists a transformation group G over E, whose orbits are the equivalence classes of A under tilde. This transformation group characterization of equivalence relations differs fundamentally from the way lattices characterize order relations. The arguments of the lattice theory operations meet and join the elements of some universe A. Meanwhile, the arguments of the transformation group operations composition and inverse are elements of a set of bijections A. Moving to groups in general, let H be a subgroup of some group G. Let tilde be an equivalence relation on G, such that a tilde be the equivalence classes of tilde, also called the orbits of the action of H on G, are the right cosets of H in G. Interchanging A and B yields the left cosets. Proof. Let function composition interpret group multiplication, and function inverse interpret group inverse. Then G is a group under composition, meaning that XAGG equals X, because G satisfies the following four conditions. G is closed under composition. The composition of any two elements of G exists, because the domain and codomain of any element of G is A. Moreover, the composition of bijections is bijective. Existence of identity function. The identity function, I equals X, is an obvious element of G. Existence of inverse function. Every bijective function G has an inverse G-1, such that G-1 equals I. Composition associates. F equals H. This holds for all functions over all domains. Let F and G be any two elements of G. By virtue of the definition of G, G equals F, and F equals X, so that G equals X. Hence G is also a transformation group because function composition preserves the partitioning of A. Related thinking can be found in Rosen categories and groupoids. Let G be a set and let tilde denote an equivalence relation over G. Then we can form a groupoid representing this equivalence relation as follows. The objects are the elements of G, and for any two elements X and Y of G, there exists a unique morphism from X to Y if and only if X tilde Y. The advantages of regarding an equivalence relation as a special case of a groupoid include, whereas the notion of free equivalence relation does not exist, that of a free groupoid on a directed graph does. Thus, it is meaningful to speak of a presentation of an equivalence relation, i.e., a presentation of the corresponding groupoid. Bundles of groups, group actions, sets, and equivalence relations can be regarded as special cases of the notion of groupoid, a point of view that suggests a number of analogies. In many contexts, quotienting, and hence the appropriate equivalence relations often called congruences, are important. This leads to the notion of an internal groupoid in a category. Lattices. The possible equivalence relations on any set X, when ordered by set inclusion, form a complete lattice, called conx by convention. The canonical map Ker x con x relates the monoid x of all functions on X and con X. Ker is surjective but not injective. Less formally, the equivalence relation Ker on X takes each function f xx to its kernel Ker f. Likewise, Ker is an equivalence relation on X caret X. Equivalence relations and mathematical logic. Equivalence relations are a ready source of examples or counterexamples. For example, an equivalence relation with exactly two infinite equivalence classes is an easy example of a theory which is omega categorical, but not categorical for any larger cardinal number. An implication of model theory is that the properties defining a relation can be proved independent of each other if and only if, for each property, examples can be found of relations not satisfying the given property while satisfying all the other properties. Hence the three defining properties of equivalence relations can be proved mutually independent by the following three examples. Reflexive and transitive. The relation on N, or any preorder. Symmetric and transitive. The relation R on N, defined as R, BAB 0, or any partial equivalence relation. Reflexive and symmetric. The relation R on Z, defined as R, A minus B is divisible by at least one of two or three, or any dependency relation. Properties definable in first-order logic that an equivalence relation may or may not possess include: the number of equivalence classes is finite or infinite. The number of equivalence classes equals the natural number n. All equivalence classes have infinite cardinality. The number of elements in each equivalence class is the natural number n. Euclidean Relations. Euclide's The Elements includes the following common notion: 1. Things which equal the same thing also equal one another. Nowadays, the property described by common notion 1 is called Euclidean. By relation is meant a binary relation, in which arb is generally distinct from brath. A Euclidean relation thus comes in two forms. Arb. The following theorem connects Euclidean relations and equivalence relations. Theorem: if a relation is Euclidean and reflexive, it is also symmetric and transitive. Proof: for a left Euclidean relation arb a c equals arb reflexive, a raised t equals bra arb, hence R is symmetric. Arb symmetry equals arb, hence R is transitive. With an analogous proof for a right Euclidean relation. Hence an equivalence relation is a relation that is Euclidean and reflexive. The Elements mentions neither symmetry nor reflexivity, and Euclid probably would have deemed the reflexivity of equality too obvious to warrant explicit mention.